All right, so we talked about ratios and proportions last time. We're going to continue talking about proportions now, and in particular, how to set them up to help find some different things. All right, some of those things are missing side lengths of a geometric figure. We want to be able to use scales to find different things in story problems and talk about some multi-step problems as well. So, to get an idea of how we need to set up our proportions to solve for what we need, we first need to understand that proportions are very flexible. Okay? So in this diagram, we know this. We know that the ratio of mn to rs, so if we compare the length of mn, which is 8, to the length of rs, which is 10, that's going to be equal to comparing the length of np, which is 4, to the length of st, which is x. Okay, well, if we wanted to find the length of st, no problem. We can just cross multiply and solve. But it actually asks for you to write 4 true proportions. There's one. How do you write another true proportion? Is there another true proportion? The proportions are a lot like equations in that you can have equivalent proportions, just like you have equivalent equations, and if they're equivalent proportions, they're going to come up with the same answer. So my question to you is, how can we rewrite this proportion? How can we create an equivalent proportion from that guy? Well, there's a lot of things we can do. Things like 10 to 8 is equal to x to 4. If we just take the reciprocal of both ratios, then it gives us the same result. That's called the reciprocal property. Okay? If we switch the means, right? And the means are these guys right here, just one of the diagonals. If we switch the diagonals, then we're still going to get the same result. It doesn't matter which diagonal you switch, right? We can even go like this. X to 4 equals, well, from the original. We can switch the means or the extremes. The extremes are the other diagonals. Again, knowing the names are not a big deal. Okay? We can do that. We can even do this. Watch this. 18 to 10 is going to be equal to 4 plus x to x. Because if we cross multiply, we get 18x equals 40 plus 10x. Subtract the 10x, and we get 8x equals 40. It's the same thing throughout this entire process. The moral of the story is this. A lot of proportions. You can set up proportions in a lot of different ways to help you find what you need. What you have to do is you have to establish a pattern for your first ratio, and then make sure you follow that pattern for the second. Right? And if you go through all of these, you'll see a pattern emerge. So our first ratio, mn to rs, had us take this measure and compare it to the corresponding side of the other triangle. We went from small triangle to bigger triangle. Then our next ratio had us do the same thing. Small triangle to bigger triangle and corresponding sides. So we followed the same pattern that the first ratio had. If we take a look at this one, right, now we're going from big to small, corresponding sides. That means my next ratio needs to go big to small, corresponding sides, and it did. If you look at this one, we're going, okay, now we're comparing the side lengths of the same triangle and making sure it's equal to comparing the corresponding side lengths of the bigger triangle. So it's establishing a similar pattern. Okay? That's the deal. All you have to do is make sure that your ratios are following a similar pattern. Okay? Now, we'll continue this conversation in terms of following a pattern in just a minute. Right now, we want to focus on making sure that we can use these proportions to help us find sides that we might need. Right, so here's a figure that actually contains two triangles, if you see it. But what we know is this proportion is true. So we need to go find the length of BA and BD. Right? Think about that for a second. How would you set that up? Okay, well, we're still just going to plug in what we know, right? BE is 18, so I'm going to kind of fill this in backwards. EC is 6. DA is 3. Now, BD, how long is BD? And you got to be careful here. The entire side of BA is X. So to find BD, we've got to subtract 3 from that X. So BD is X minus 3. There's the proportion that you want to cross multiply and solve. This is 54, 6x minus 18, right? Add 18 to both sides. So 6x equals 72, divide by 6, and x is 12. Okay? Now, great, x is 12. What's that mean? We need to find the length of BA. Like I said, BA is all of x. So BA is just going to be 12. BD is x minus 3, so it's 12 minus 3, which is going to be 9. Okay? Just plugging in what we know. All right? All right, scales. Scale drawings is a drawing that is the same shape as the object it represents. We use scale drawings if we want to make some, if we want to take something and blow it up so we can see it easier. Take something really, really big and scale it down to make it easier to handle. Okay? When you do a scale drawing, it's not just any drawing, it's a scale drawing, and so that means everything is to scale. Everything is proportional. For example, the blueprint shows a scale drawing of a cell phone. The length of the antenna, and I know cell phones don't have antennas anymore, so just bear with me. The length of the antenna on the blueprint is 5 centimeters. The actual length of the antenna is 2 centimeters. What is the scale of the blueprint? Well, the scale of the blueprint needs to tell us how much one unit in one, whether it's the drawing or the actual shape, how much one unit is equal to in the other item, if that makes any sense. Okay? So since the length of the antenna in the blueprint is 5 centimeters, I'm going to compare that to 2 centimeters of the actual antenna. Well, if we reduce this, we get 5 to 2. I'm going to go ahead and divide both of these by 2 so that my denominator becomes 1. We get 2.5 to 1. So what that means is, and we can keep the units in actually, for every 1 centimeter of the actual phone, remember that this was the drawing compared to the actual phone. For every 1 centimeter of the actual phone, we're going to make that 2.5 centimeters in the drawing. So we're blowing it up. Okay? That's our scale. All right, we're going to use the scale to find the actual distance in this map. We want to measure this distance and then set up a proportion. So, how to use this scale to find the actual distance from Pocahontas to Algona. Okay? Well, way back when, in the olden days, before Google Maps, this is what we had to do, right? So we needed to measure the actual distance, and we're not talking about the driving distance, I'm talking about the actual distance, right? So we had to find the actual distance on the map distance from Pocahontas to Algona. And if you were to measure that, pull out a ruler and measure that, you should get 1 1/4 inches or 1.25 inches. Okay? Now, the scale of the map will help us out. 1 inch in the map corresponds to 26 miles of actual distance. Well, that scale needs to apply for anything that we measure in the map. So that ratio should be equal to the ratio of comparing the actual map distance, which is 1.25 inches, to the actual distance between the two cities, which we don't know. So that's going to be x. So again, we've kind of already been given a pattern in our first ratio. We want to go inch to miles, so basically map distance to actual distance, and the scale gives us a ratio already, 1 inch to 26 miles. That way we know how to set up our second ratio, which is the same pattern, right? Map distance to actual miles. So here's our proportion. We're going to cross multiply and solve. We get 1 times x is x, 26 times 1.25 is 32.5. So there's actually 32.5 miles between Pocahontas and Algona. Okay? That's how we use this scale. All right. Now, setting up proportions all on your own. Okay, you buy a 3D scale model of the Reunion Tower in Dallas, Texas. The actual building is 560 feet tall. Your model is 10 inches tall, and the diameter of the dome on your scale model is about 2.1 inches. Now what I'd like for you to do is go ahead and create a proportion that helps you find the diameter of the dome based on what we've talked about. And then we're going to talk about figuring out about how many times as tall as your model is the actual building. But come up with the proportion first to solve for part A. Just a warning, your proportion might be different than mine. But we'll talk about how to make sure yours is okay in just a second. So give it a shot, stop the video, start it back up and see if your proportion makes sense. Okay, so the way I see this is this. I'm going to compare height of the model to height of the actual building. Okay, that's how I want to set up my pattern. I want to go model to actual building. And so I can do it for the heights, and I can actually do that for the diameter of the domes. Go from model, which is 2.1. Ugh, can't write. To diameter of the actual dome, which we don't know, and that's going to be x. You may have seen this differently. Okay? As long as your pattern, as long as you establish a pattern in your ratio for the first one, and the second one follows the same suit. So I wanted to compare the heights and then compare the diameters. And I went scale to building equals scale to building. I had some people today say they wanted to go 10 to 2.1 because that's inches to inches, and we're going height to dome. So that means my next ratio for the actual tower needs to go height to dome. And then you can cross multiply and solve. But we're kind of getting into the same issue as the first example, where all of these proportions end up being the same. So as long as you're careful about making sure that your ratios are following a similar pattern, then you should be in fine shape. So the diameter of that dome apparently is 117.6 feet. Now the next question says, about how many times as tall as your model is the actual building? Okay. Well, that's a ratio. Remember we talked about a simplified ratio should tell you how much bigger or how much longer one thing is compared to another. So about how many times as tall as your model is the actual building? Well, we need to compare the height of the actual building to the height of the model. But you have to remember that these guys are not in the same units. They've got to be in the same units. So we need to convert. I'm going to convert feet to inches. So I'm going to put feet in the denominator of this conversion fraction, inches up here. And 1 foot, there's 12 inches. So I need to take 560 times 12, which is 6720, and divide that by 10 to get 672 to 1. That's our simplified ratio, which means that the building is 600 and, oops, I wrote that backwards. 672 times taller than the model is. Okay? And again, that's kind of what we did with the last homework assignment. Now, that's different than trying to find the scale of a map. So that's what your next example is all about. Two cities are 96 miles from each other, and they're 4 inches apart on a map. What's the scale of the map? Here, we don't actually want to convert to get to the same units. I'm not trying to find out how many times longer the actual distance is from the map distance. I just want to know the scale of the map. How many miles corresponds to 1 inch in the map? So I actually want to keep the units exactly the way they are, but I'm still going to write this as a ratio and then simplify it down as much as I can. I want to divide this out. I want to divide 96 by 4 so that I can get my denominator to be 1. When you do, you get 24. So every inch on the map corresponds to 24 miles of actual distance. That's different than the last question we had to answer. Okay, one more here. Your friend has a model of the Reunion Tower. So we're back to the Reunion Tower. But your friend's model is 14 inches tall. If it's going to be a scale model, what does the diameter of the dome for your friend's model need to be? Okay, well again, you set up your proportion so that your ratios are following a similar pattern. I would still go height to height. That makes sense to me. So 14 inches is the height of the model. 560 feet is the height of the actual tower. Back up and make sure. Yep. Okay. Now that has to be equal to comparing the diameters of the dome. I don't know the diameter of my friend's dome, but I do know the diameter of the actual dome is 117.6 feet. Now I'm going to cross multiply. And then divide by 560. So the diameter of my friend's dome, wait a minute, does that make any sense here? Let's make sure our answer makes some sense. Okay, yeah, the diameter of my scale model was 2.1 inches, and we've got 2.94 inches for my friends. And it should be a little bit bigger because his tower is taller. So there you go. Okay? That's it. Your homework's out in Canvas. Make sure you get that done by next time.